Evet, değerli Art TV izleyenleri, bugün 20 Aralık 2021 Pazartesi. Şimdi bir başka konuya geçmek istiyorum. Ee, Güneş sisteminin e, bütünü itibariyle e, yapılan keşiflerden bahsettik. Burada bir de Wikipedia'da Güneş'in kürelerinin yapısı ve özellikleri hakkında epeyce kapsamlı, tafsilatlı bir İngilizce makale var. Şimdi onu önce bir okutalım Microsoft David'e. Sonra da sabırla dinlerseniz ben elimden geldiğince onu çevirerek yorumlamayı deneyeceğim. Ama önce Microsoft David konuşsun.
From Wikipedia, the free encyclopedia. For other uses, see sun, disambiguation, and the sun, disambiguation. Sun. True color image taken in 2019 in the entire spectrum of visible light using a solar filter. False color image taken in 2010 as seen in ultraviolet light, wavelength of 30.4 nanometers. Names. Sun, Sol /SL /1 Sol, Helios /Hila /2. Adjectives. Solar /Solar /3. Observation data. Mean distance from Earth. 101.496 times 108 km for 8 minute 19, south at light speed. Visual brightness, V. 26.745.
Negatif.
Absolute magnitude, 4.835. Spectral classification, G2V6. Metallicity, Z equals 0.01227. Angular size, 31.6 to 32.7 minutes of arc 8 0.527, 0.545 degrees. Orbital characteristics. Mean distance from Milky Way core, 2.7 times 1017 km 29,000 light years. Galactic period, 2.25 to 2.50 times 108 year. Velocity, 251 kilometers per second, orbit around the center of the Milky Way, 20 kilometers per second, relative to average velocity of other stars in stellar neighborhood, 370 km/s9, relative to the cosmic microwave background. Physical characteristics. Equatorial radius, 695,700 km 10 696,342 km 11,109 times Earth radii 12. Equatorial circumference, 4.379 times 106 km 12,109 times Earth 12. Flattening, 9 times 10⁶. Surface area, 6.09 times 1012 km 212.12,000 times Earth 12. Volume, 1.41 times 1018 km 312.1,300,000 times Earth. Mass, 1.9885 times 1030 kg 5332,950 Earth's 5. Average density, 1.408 g/cm 351213 0.255 times Earth 512. Center density, modeled, 162.2 g/cm 3512.4 times Earth. Equatorial surface gravity, 274 m/s2528 times Earth 12. Moment of inertia factor, 0.075, estimate. Escape velocity, from the surface, 617.7 km/s1255 times Earth 12. Temperature. Center, modeled 1.57 times 107 K5 photosphere, effective 5772 K5 corona, 5 times 106K. Luminosity, LSAL. 3.828 times 1026 W5 3.75 times 1028 LM 98 LM/W. Efficacy. Color, BV. 0.63. Mean radiance, ISOL. 2.009 times 107 WM2 SR1. Age. 4.6 billion years, 4.6 times 109 years, 1415. Rotation characteristics. Obliquity. 7.25 degree 5 to the ecliptic, 67.23 degree to the galactic plane. Right ascension off North Pole 16. 286.13 degree 19 4 minutes 30 s. Declination off North Pole. Plus 63.87 degree 63 degree 52 north. Sidereal rotation period, at equator. 25.05 d5. At 16 degrees latitude. 25.38 d5 25 d9 h7 minutes 12 s16. At poles. 34.4 d5. Rotation velocity, at equator. 7.189 times 103 km/h12. Photospheric composition, by mass. Hydrogen. 73.46% 17. Helium. 24.85%. Oxygen. 0.77%. Carbon. 0.29%. Iron. 0.16%. Neon. 0.12%. Nitrogen. 0.09%. Silicon. 0.07%. Magnesium. 0.05%. Sulfur. 0.04%. The Sun is the star at the center of the solar system. It is a nearly perfect ball of hot plasma 1819 heated to incandescence by nuclear fusion reactions in its core, radiating the energy mainly as visible light, ultraviolet light, and infrared radiation. It is by far the most important source of energy for life on Earth. Its diameter is about 1.39 million kilometers, 864,000 miles, or 109 times that of Earth. Its mass is about 330,000 times that of Earth, and it accounts for about 99.86% of the total mass of the solar system. Roughly 3/4 of the Sun's mass consists of hydrogen, 73%, the rest is mostly helium, 25%, with much smaller quantities of heavier elements, including oxygen, carbon, neon, and iron. 21. According to its spectral class, the Sun is a G-type main sequence star, G2b. As such, it is informally, and not completely accurately, referred to as a yellow dwarf. Its light is closer to white than yellow. It formed approximately 4.6 billion A1422 years ago from the gravitational collapse of matter within a region of a large molecular cloud. Most of this matter gathered in the center, whereas the rest flattened into an orbiting disk that became the solar system. The central mass became so hot and dense that it eventually initiated nuclear fusion in its core. It is thought that almost all stars form by this process. The Sun's core fuses about 600 million tons of hydrogen into helium every second, converting 4 million tons of matter into energy every second as a result. This energy, which can take between 10,000 and 170,000 years to escape the core, is the source of the Sun's light and heat. When hydrogen fusion in its core has diminished to the point at which the Sun is no longer in hydrostatic equilibrium, its core will undergo a marked increase in density and temperature while its outer layers expand, eventually transforming the Sun into a red giant. It is calculated that the Sun will become sufficiently large to engulf the current orbits of Mercury and Venus, and render Earth uninhabitable, but not for about 5 billion years. After this, it will shed its outer layers and become a dense type of cooling star known as a white dwarf, produce energy by fusion,
Biraz kısar
but
mısın
still glow
lütfen?
and give off heat from its previous fusion.
Kafamda zorluyor, başım
The enormous effect of the sun on Earth has been
İçeri git
recognized since
istemiyorsan.
prehistoric
İçeriden
times.
duyulmuyor.
The sun was thought of by some cultures as a deity. The synodic rotation of Earth and its orbit around the sun are the basis of some solar calendars. The predominant calendar in use today is the Gregorian calendar, which is based upon the standard 16th century interpretation that the sun's observed movement is primarily due to it actually moving 23. Contents: 1. Name and etymology. 2. General characteristics. 3. Sunlight. 4. Composition. 4.1 Singly ionized iron group elements. 4.2 Isotopic composition. 5. Structure and fusion. 5.1 Core. 5.2 Radiative zone. 5.3 Tachocline. 5.4 Convective zone. 5.5 Photosphere. 5.6 Atmosphere. 5.7 Photons and neutrinos. 6. Magnetic activity. 6.1 Magnetic field. 6.2 Variation in activity. 6.3 Long-term change. 7. Life phases. 7.1 Formation. 7.2 Main sequence. 7.3 After core hydrogen exhaustion. 8. Motion and location. 8.1 Motion in the solar system. 8.2 Orbit in Milky Way. 8.3 Galactic location. 9. Theoretical problems. 9.1 Coronal heating problem. 9.2 Faint young sun problem. 10. Observational history. 10.1 Early understanding. 10.2 Development of scientific understanding. 10.3 Solar space missions. 11. Observation and effects. 12. Planetary system. 13. Religious aspects. 14. See also. 15. Notes. 16. References. 17. Further reading. 18. External links. Name and etymology.
Extraterrestrial links.
The English word sun
19
developed from Old
extraterrestrial
English sun.
links.
Cognates appear in other Germanic languages, including West Frisian sin, Dutch song, Low German sun, Standard German son, Bavarian suna, Old Norse suna, and Gothic sunno. All these words stem from Proto-Germanic *sun and 2425. This is ultimately related to the word for sun in other branches of the Indo-European language family, though in most cases a nominative stem with an L is found, rather than the genitive stem in N, as for example in Latin sol, ancient Greek lambda iota omicron, Helios, Welsh hall, and Russian, Salm Seb, pronounced sunsi, as well as, with asterisk LR, Sanskrit, Svar, and Persian, Atar. Indeed, the L stem survived in Proto-Germanic as well, as asterisk Saulan, which gave rise to Gothic Solurl, alongside Sunno, and Old Norse prosaic Sol, alongside poetic Suna, and through it the words for sun in the modern Scandinavian languages, Swedish and Danish Solin, Icelandic Solin, etc. 25. In English, the Greek and Latin words occur in poetry as personifications of the sun, Helios, /Ila/ and Sol, /SL/ 21, while in science fiction Sol may be used as a name for the sun to distinguish it from other stars. The term Sol with a lowercase s is used by planetary astronomers for the duration of a solar day on another planet such as Mars 26. The principal adjectives for the sun in English are sunny for sunlight and, in technical contexts, solar, /solar/, 3 from Latin sol 27, the latter found in terms such as solar day, solar eclipse, and solar system, occasionally sol system. From the Greek helios comes the rare adjective heliac, /hilix/, .28. The English weekday name Sunday stems from Old English Sunanda ex sun's day, a Germanic interpretation of the Latin phrase die solis, itself a translation of the ancient Greek muro alpha lambda omicron upsilon, hemera heliou, day of the sun 29. General characteristics. The Sun is a G-type main sequence star that constitutes about 99.86% of the mass of the solar system. The Sun has an absolute magnitude of plus 4.83, estimated to be brighter than about 85% of the stars in the Milky Way, most of which are red dwarfs. 3031. The Sun is a population I, or heavy element rich B star. 32. The formation of the Sun may have been triggered by shock waves from one or more nearby supernovae. 33. This is suggested by a high abundance of heavy elements in the solar system, such as gold and uranium, relative to the abundances of these elements in so-called population II. Heavy element poor stars. The heavy elements could most plausibly have been produced by endothermic
Kainattaki
nuclear
defin
reactions
haritasını
during a
veriyor.
supernova, or by
Altın var.
transmutation through neutron
Altın
absorption within a
uranyum.
massive second-generation star. 32. The Sun is by far the brightest object in the Earth's sky, with an apparent magnitude of 26.74. 34. 35. This is about 13 billion times brighter than the next brightest star, Sirius, which has an apparent magnitude of 1.46. 1 astronomical unit, about 150 million kilometers, 93 million miles, is defined as the mean distance of the Sun's center to Earth's center, though the distance varies as Earth moves from perihelion in January to aphelion in July. 36. The distances can vary between 147,098,074 kilometers, perihelion, and 152,097,701 kilometers, aphelion, and extreme values can range from 147,083,346 kilometers to 152,112,126 kilometer. 37. At its average distance, light travels from the Sun's horizon to Earth's horizon in about 8 minutes and 19 seconds, while light from the closest points of the Sun and Earth takes about 2 seconds less. The energy of the sunlight supports almost all life seen on Earth by photosynthesis. 38. And drives Earth's climate and weather. The Sun does not have a definite boundary, but its density decreases exponentially with increasing height above the photosphere. 39. For the purpose of measurement, the Sun's radius is considered to be the distance from its center to the edge of the photosphere, the apparent visible surface of the Sun. 40. By this measure, the Sun is a near-perfect sphere with an oblateness estimated at 9,041,041, which means that its polar diameter differs from its equatorial diameter by only 10 kilometers, 6.2 miles. 42. The tidal effect of the planets is weak and does not significantly affect the shape of the Sun. 43. The Sun rotates faster at its equator than at its poles. This differential rotation is caused by convective motion due to heat transport and the Coriolis force due to the Sun's rotation. In a frame of reference defined by the stars, the rotational period is approximately 25.6 days at the equator and 33.5 days at the poles. Viewed from Earth as it orbits the Sun, the apparent rotational period of the Sun at its equator is about 28 days. 44. Viewed from a vantage point above its north pole, the Sun rotates counterclockwise around its axis of spin. 45. Sunlight. Main article, Sunlight. The Sun, as seen from the Earth's surface. The solar constant is the amount of power that the Sun deposits per unit area that is directly exposed to sunlight. The solar constant is equal to approximately 1,368 W/m2, watts per square meter, at a distance of 1 astronomical unit, O, from the Sun, that is, on or near Earth. 46. Sunlight on the surface of Earth is attenuated by Earth's atmosphere, so that less power arrives at the surface, closer to 1,000 W/m2. In clear conditions when the Sun is near the zenith. 47. Sunlight at the top of Earth's atmosphere is composed, by total energy, of about 50% infrared light, 40% visible light, and 10% ultraviolet light. 48. The atmosphere in particular filters out over 70% of solar ultraviolet, especially at the shorter wavelengths. 49. Solar ultraviolet radiation ionizes Earth's day-side upper atmosphere, creating the electrically conducting ionosphere. 50. The Sun emits light across the visible spectrum, so its color is white, with the CIE color space index near 0.3, 0.3. When viewed from space or when the sun is high in the sky. The solar radiance per wavelength peaks in the green portion of the spectrum when viewed from space. 51-52. When the sun is low in the sky, atmospheric scattering renders the sun yellow, red, orange, or magenta. Despite its typical whiteness, most people mentally picture the sun as yellow. The reasons for this are the subject of debate. 53. The sun is a G2V star, with G2 indicating its surface temperature of approximately 5,778 K, 5,505 degrees Celsius, 9,941 degrees Fahrenheit, and V. That it, like most stars, is a main sequence star. 54-55. The average luminance of the sun is about 1.88 gigacandela per square meter, but as viewed through Earth's atmosphere, this is lowered to about 1.44 GCD/M2E. However, the luminance is not constant across the disk of the sun, due to limb darkening. Composition. False color wiggle animation of the sun. Normally the sun does not make gamma rays, but a flare on June 15, 1991, caused this gamma ray observation by the Cantel instrument on the Compton Gamma Ray Observatory. Neutrons from the sun collided with the interstellar medium to produce gamma rays. 1973 solar flare as recorded by Skylab. See also, molecules in stars. The sun is composed primarily of the chemical elements hydrogen and helium. At this time in the sun's life, they account for 74.9% and 23.8% of the mass of the sun in the photosphere, respectively. 56 All heavier elements, called metals in astronomy, account for less than 2% of the mass, with oxygen, roughly 1% of the sun's mass, carbon, 0.3%, neon, 0.2%, and iron, 0.2%, being the most abundant. 57. The sun's original chemical composition was inherited from the interstellar medium out of which it formed. Originally it would have contained about 71.1% hydrogen, 27.4% helium, and 1.5% heavier elements. 56 The hydrogen and most of the helium in the sun would have been produced by Big Bang nucleosynthesis in the first 20 minutes of the universe, and the heavier elements were produced by previous generations of stars before the sun was formed, and spread into the interstellar medium during the final stages of stellar life and by events such as supernovae. 58. Since the sun formed, the main fusion process has involved fusing hydrogen into helium. Over the past 4.6 billion years, the amount of helium and its location within the sun has gradually changed. Within the core, the proportion of helium has increased from about 24% to about 60% due to fusion, and some of the helium and heavy elements have settled from the photosphere towards the center of the sun because of gravity. The proportions of metals, heavier elements, is unchanged. Heat is transferred outward from the sun's core by radiation rather than by convection, see radiative zone below, so the fusion products are not lifted outward by heat, they remain in the core. 59 And gradually an inner core of helium has begun to form that cannot be fused because presently the sun's core is not hot or dense enough to fuse helium. In the current photosphere, the helium fraction is reduced, and the metallicity is only 84% of what it was in the protostellar phase, before nuclear fusion in the core started. In the future, helium will continue to accumulate in the core, and in about 5 billion years this gradual build-up will eventually cause the sun to exit the main sequence and become a red giant. 60. The chemical composition of the photosphere is normally considered representative of the composition of the primordial solar system. 61 The solar heavy element abundances described above are typically measured both using spectroscopy of the sun's photosphere and by measuring abundances in meteorites that have never been heated to melting temperatures. These meteorites are thought to retain the composition of the protostellar sun and are thus not affected by the settling of heavy elements. The two methods generally agree well. 21. Singly ionized iron group elements. In the 1970s, much research focused on the abundances of iron group elements in the sun. Day 62-63 Although significant research was done, Until 1978 it was difficult to determine the abundances of some iron group elements, e.g. cobalt and manganese, via spectrography because of their hyperfine structures. 62. The first largely complete set of oscillator strengths of singly ionized iron group elements were made available in the 1960 S64 and these were subsequently improved. 65. In 1978, the abundances of singly ionized elements of the iron group were derived. 62. Isotopic composition.
Burada bir ara verelim ve Microsoft David'e teşekkür edelim. Şimdi ben de dilim döndüğünce kısım kısım şu okunmuş kısmı bir tercüme edip yorumlamaya gayret edeyim.